Our next presentation is another case study, and this time is for a project in New York at the very top of the Vanderbilt Tower. And it is also another structural application case study. I cannot see our speaker. Oh, here you are. Sorry, I'm blinded. I'm terribly sorry. And here to talk about it is Timo Bühlmeier. And he's lead concept designer and design development manager with Joseph Gardner, a division of Permastelisa. And the floor is yours. Thank you.
Thank you for your introduction. So it's all about structural glass today. So welcome to the next session. I hope you don't get confused. The title changed a little bit. Structural glass assembly with a novel mortise and tenon joint. So what we are looking today are the levitation ledges of the One Vanderbilt Tower, located in 300 meters height above ground in New York City. These structural glass assemblies are integrated in a unitized facade. And the tower itself, on the left-hand side, is designed by the architectural office KPF, Kohn Pedersen Fox, located very closely to the Grand Central Terminal. My presentation is basically in 3 parts. Why are the levitation ledges such a design challenge? And how did we design it and verify it? The installation itself and the conclusion will be drawn. The levitation ledges are located here on the very left. They are part of the observation deck of the One Vanderbilt Tower. It's the 59th floor is an outdoor observation deck. 57 and 58 are indoor observation decks. All are publicly accessible. And on the right-hand side, you see an image of the interior, because this is an art installation from Kenzo Digital. It's a kind of signature feature melting the sky, the city, and art in an interactive experience with all those mirrors. To give you an impression, I show this small movie, how it feels like being up there and how it feels like walking out on the structural glass assembly. We started the project with a very clear, crystal clear design brief, I must say. It was about creating absolute transparent structure with unobstructed views to Manhattan skyline. So why is it a challenge? We had previous projects like the Skywalk in Alberta or the Ritz-Carlton Bridge, but all of them use secondary elements for such a critical accessible floor, or they used point connections for such structures. So how to achieve an absolutely minimal structure with no visible connection elements and nothing obstructing? In the beginning, we started with some rough conceptual schemes, but all of them had their drawbacks. The curved corner panels on the left-hand side with its distortion effect somehow compromised the clear view, even if they were very stiff. Intermediate members also obstructed a free view in scheme 2 and 3. And in scheme 4, you see cantilevering glass from the top, which meant relatively high connection forces at the top and stresses. And in 5, we tried to connect the structure on the level beyond, and that imposed or attracted somehow building movements, which were not really beneficial. So it turned out to be the best using the lower structure, a self-contained system, with perimeter framing. The next step was, I called it, we balanced performance versus design quality. Because the initial step was we relocated the ledges on the tower itself in an area with reduced wind loads. That facilitates everything a lot. In terms of glass, initially they thought about using IGUs. We simplified using laminated glass, all backed up with MEP and thermal performance conceptually. For a clear view, we needed anti-reflective layers, anti-reflective coating, sorry, on the outer side and on the inside. What else? The floor, for example, had to be very transparent. We applied a ceramic dot frill pattern instead of acid-etched glass, which is way more transparent. And finally, we introduced a circumferential movement joint, which allowed to control the deflections within the structure and to minimize joints. But the fundamental question stayed, how can we achieve ultimate transparency in the connections? So we introduced the mortise and tenon joint, which is a joint known from woodworking or timber constructions. To transfer the success of this joint in structural glass are really evident because it's a secure connection, it's very strong and simple. The joint consists basically of two components, as you can see on the right-hand exploded view, a tenon tongue, which is a protrusion of the glass edge, and it fits perfectly in the vertical panel where the mortise hole is cut out and sits there on a setting block. The big benefit is load transfer in the central axis without any asymmetries we are struggling often with. And on the right-hand side, the wind loads are transferred via a continuous silicon joint along the glass edge. Looking at some principal stress plots, obviously we had increased stresses around the mortise and tenon joint, predominantly in areas of the curved edges, especially on the tenon tongue. Roughly in a magnitude of 10 megapascal, which doesn't seem a lot, but we worked here with 1 out of 1,000 breakage probability, and the allowable stress there is around 23 megapascal. So the local stresses, is there a pointer? No. The local stresses you can see here and here are can be explained by the local load transfer, but also by so-called carding moments. They are often mentioned in the bridge design from Jörg Schleich and Hans Schober. So, but how did we get there? We had several potential options, but all had their drawbacks. Like on the top left, the through-bolted connection was architecturally not desired as it adds an element, connector. Same thing with the adhesive connection. It also needs a connector and had the additional drawback of missing durability track record and safety, obviously. So we thought about embedded laminated connections. You still have some visible elements, and there's also a little drawback from the technical side, at declining load carrying capacity, at increasing temperatures, mentioned by Santasiero. So the mortise and tenon joint was the most convincing connection typology for such a critical structure. No additional visible elements, especially from the inside, as you keep really one sideline from the interior. And structurally, the previously mentioned direct load transfer in the connection. Also, it could better compensate tolerance, production and fabrication tolerances, which is an issue on all the other connections. Additionally, we did a very rough comparison between the bolted connection and the mortise and tenon joint and find out at roughly same size, the stresses in the mortise and tenon joint are 2.5 times less compared to the bolted connection. The overall structure, especially the critical nature of an all-glass application, required a well-thought engineering approach. It's here more about balancing costs, reliability, and risk. So a sound safety concept was needed, consisting of load carrying capacity, impact resistance, and post-breakage scenarios. We tested them later on, the load carrying capacity with 2 times the design load, all elements, all connections, impact testing according CWCT TN 66 and 76, and the post-breakage scenarios with a duration of 1 minute and 24 hours. 1 minute is the assumed evacuation time. The major scenarios were the floor panel fully broken here on the lower side, then a fully broken front panel, and even 2 fully broken front panels were tested. So the all-encompassing engineering approach was based on the safety concept, which we verified with an entire finite element model, which was in the end confirmed by a full-scale mock-up within our facilities to prove the structural integrity of the system. In the final configuration, the system itself was a glass box 5.3 meters high, 3.7 meters wide, 1.5 meters deep, and it is top hung from RHS 250 sections via bolted connections, and the lower part provides substantial in-plane capacity for the movements and deflections occurring. In the back, all the structure is connected with a structural silicon seal. It's top supported on structurally determined on the red dot locations on the top level and released on the lower level, allowing in-plane facade movements. The loads of the floor were transferred directly up in the vertical panel, then on the top back to the structure and the primary structure, obviously causing some deflections in the cantilever. The load path for the wind loads is the following. They are introduced in the bolted connection at the top, at the continuous silicon joint at the bottom. In the case of a side wind on the side panel, the front panel acts as a beam supported by the bolted connection, and below and in the lower end by the continuous structural silicon joint. On the right-hand side, you see the further load transfer through the floor panel with its diaphragm action back to the steel framing and up again in the structure. Some specifics about the design. Obviously, we tried to hide everything, every functional structural element. All the drainage channels were integrated in the facade line, the structure itself, the vertical steel frame, as well as the movement joints. The only visible element was in the end the cantilever to the front, and obviously some structural glazing joints. Here the previously mentioned PMU we did in our facilities. It wasn't only about testing, it was also about verifying our installation sequences and to double check our structural results with deflection sensors. It's quite impressive, the load capacity test here, 2 times the design load, 2 times 100 PSF, which equals 72 persons or 2 elephants. We shouldn't tell that an aeronautic engineer. Here the impact testing according CWCT, which we passed successfully. And all critical elements have been tested until failure or broken. So the vertical panel without vertical silicon joints, all lights broke at 2 times the wind load. The floor panel, the load capacity of the floor panel was tested with half of the 100 PSF with all lights broken. And the load carrying capacity in plane directions for the front panel was tested with 6 times the wind load, and then it clashed in the mortise and tenon joint. That can be explained because we cut off the silicon joint before doing this test. The installation. Obviously also a challenge in 300 meters height to set up a working platform, to lift up all the materials. I just want to point out here some fundamental steps. In image 1 in the center, you can see how we applied some dummy weights to control the deflection and to simulate the dead load of the glazing, to install them precisely. Then in number 2, you can see the installation of the first floor panel. It needed a temporary support up to the cantilever, which was quite a bold installation step. Then we could carry on here in the center on image 3 with the side panels and front panels and the top panel. Finally, in the right image, you can see how we clamped together all the structure to do a final control survey and do some fine adjustment on site, and then finally sealing everything. The last step was getting on the floor a sacrificial layer, which you typically do on such structures. To conclude, with the mortise and tenon joint, we have a very strong and minimized connection. I think, I don't know if it's novel, but it's not very often used. Then the key to transparency for us was the balance between performance and design quality, smart load paths, and the clever combination of all connection methods. In addition, a robust and safe design could be achieved with a dedicated design approach. And in the end, the visitors can reimagine thrill and enjoy the unobstructed view to Manhattan skyline. Thank you.